All right, hello, Calculus AB. Here we are for our related rates video, the first 2 pages. So this is 5.6, and this is where we will pick up semester 2, related rates. So we're going to see what happens to one rate as another one changes. So it's a little bit similar to differentials. Except you'll see the difference. We're going to have to do some implicit differentiation. Okay, so you've seen how the chain rule can be used to find dy dx or y prime implicitly. Another important use of the chain rule, or really implicit differentiation, is to find the rates of change. All right, so how does one rate change as another one is changing? Of 2 or more related variables that are changing with respect to time. So there's a big difference. In the differentials before, we were just doing dy dx. But now we're going to be doing dt. All right, we're going to be differentiating with respect to time, so dt here. Related rates is the study of how fast one quantity is changing as another quantity changes. Because the 2 are related somehow to each other. So like in an area, of a circle, radius and area are related to each other. So related in somehow in a formula. Many problems will either utilize similar triangles, or you can Pythagorean theorem. We'll have our geometry formulas too that might be used. This, that, and the other. So just the way we're going to relate our 2 variables is to have a formula to differentiate. So example 1 says, suppose x and y are both differentiable functions. Gosh, I can't talk. Suppose x and y are both differentiable functions of t and are related by this, parabola, y equals x squared plus 3. So find dy dt. So that's huge right there to notice that we're differentiating with respect to time. When x equals 1, given that dx dt is equal to 5 when x equals 1. So this is similar to our differentials, right? We're looking for the rate of y given, this differential. So it's very similar, except what changes it is this with respect to time. So this makes the differentiation not where we can just multiply up dx, because we don't want to split at that with this differentiation with respect to time. But the idea is the same. We know a rate, and we want to see how the other rate is changing. With differentials, we knew the dx. We wanted to see the dy, so we moved up the dx. Here, we want to get the dx over dt, so we won't be cross-multiplying it up. But again, just the changing quantity as another one is changing, idea is the same. So the way we start this is to implicitly differentiate because we are differentiating with respect to t. So when I differentiate y with respect to t, we're just going to get 1. So, there's a 1 there, but we don't write that. And this is going to be, we differentiate the parabola. And so this will equal 2x. And I just differentiated x with respect to t, so that implicit piece comes in. And then when I differentiate a constant, of course, I get 0. All right, so dy dt equals 2x dx dt, and now we just sub in. So when x equals 1, we get 2 times 1, and dx dt was 5. So this is just 10. And no units in this problem. So that is related rates. All right, so let's look at some problems here. Pebbles dropped in a calm pool and causing ripples in the form of concentric circles. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? So the given rate, 1 foot per second, and that's your radius. So that is dr dt equaling 1. All right, and we want to find the area. How is it changing? So we want to find dA dt. And when are I call this sort of the time stop. When are we stopping the problem to assess this? Stop the problem when the radius is 4. Stop the changing when the radius is 4. So the related rates, how do I relate these rates? Pi r squared. Differentiate a, so that's just 1 dA dt. And differentiate pi r squared. So that is 2r pi dr dt. Okay? And we just sub in 2 times stop. The radius is 4. Pi given dr dt was 1 foot per second. So this is 8 pi feet squared per second. So area is measured in feet squared, and it's a rate, so it's per time. All right, so in a complete sentence, when the radius is equal to 4 feet, the area is increasing because it's positive. As the radius increases, the total area increases. That should make sense at a rate of 8 pi feet squared per second. All right, so some helpful hints on related rates. Identify all the given quantities and quantities to be determined. Label any links, make a sketch, and label any links that remain constant. Okay, this is important. You want to make sure when you have something that's constant, you know, calculus is going to differentiate that to 0. So, you know, as always, constants aren't changing. So calculus is all about change. So if you have something that's constant, keep that in mind. That'll differentiate to 0. Label the changing links with variables. Write an equation for the sketch that relates them. All right. Take the derivative of the equation with respect to time. So this will end up being implicit. All right. Only after. This is important. After taking the derivative, then you want to substitute in. The given numbers. Anything that is changing in the problem, do not substitute until after you have gotten your change equation, which is your derivative. So anything that's constant, you can sub in at the beginning because it's not going to change. It's just going to zero out. You can sub this in. But anything that the radius is changing, the area is changing, don't sub anything into the equation that's going to change until you get your change equation, which is your derivative. All right. Next one. Air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. So always use your units to help you. Cubic feet is volume. So my given rate then is dV dt. Derivative of volume with respect to time, that rate is 4.5. And I just put my units in at the end. Find the rate of change of the radius. Okay, so we want dr dt when the radius is 2 feet. That's our time stop. We're going to stop the problem so that we're blowing up this balloon. The volume is obviously changing as the radius changes. It's getting bigger and bigger. Those my circles aren't so great over there, but that's what's happening. All right, so everything's changing here. There's no constants. So let's start our process. Okay, equation then, for a sphere, the volume of a sphere is 4 over 3 pi r cubed. Okay, so let's dV dt. We haven't had to use any of our derivative rules here. These have all been pretty simple problems here, monomials. I mean, we haven't had to use product or quotient or anything, but that's coming. For us, don't forget your dr dt. Every variable is going to get an implicit notation on it. Just every time you have a variable, just get that d, whatever the variable is, over dt into the problem. Okay, that cancels nicely. Let's sub 4.5 equals 4 pi r. Time stop. and dr/dt is what we're looking for. So this time we got to do a little algebra. 4.5 over 16 pi is our dr/dt. Okay, so that is going to calculate to 4.5 divided by 16 pi. Our dr/dt. All right, let's write our sentence. When the radius is 2 feet, this is positive. The radius is increasing. Increasing at a rate of 0.090 cubic feet per minute. Okay, I think that's good. That all makes sense. Okay, last one here for this part one of related rates, the first 2 pages of related rates. An inverted conical tank is being filled with water at a rate of 12 cubic meters per hour. Okay, so that's our dV dt. Let your units tell you what you've been given. 12. The tank is 20 meters high and the radius of base is 5 meters. So this is tank info. Okay, that's just tank info. How fast is the water level rising when the water is 8 meters deep? Okay, so how fast is the water level rising? So the water's going up, 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 up. So that is a height. So we want dH dt. And our time stop is height of 8. Okay, so we're going to take our cone here and do our volume of a cone. So we need the base, pi r square. We need to raise it by the height. So that takes that space of the base, and we just, accumulate by the height. That would be a cylinder. And then a cone, we get rid of all of this excess, and that's only 1/3 is left here. So this formula is 1/3. Okay? So, what am I going to do here? Okay, so don't write this right now, but if you were to, let's maybe split it here, do the product rule here, dv dt, 1/3 pi r squared, differentiate the h to dh dt, and then you get 2/3 r dr dt, and then leave the h alone. So when you go to sub in, you've got a dv dt, perfect, 1/3 great, pi great, r, I don't know the radius to plug in here, so that might be something I could use here. This is going to be 20, and this is going to be 5. So, that looks like 1/4 of a relationship. We're going to look at some similar triangles. So when we're 8, this is probably going to be 2. So I can probably figure out that that's going to be 2 squared, so that's good. dH/dt is what I'm looking for, and then plus 2/3 pi r. Again, I can do dr dt, and then height is 8. So this right here, I have no capabilities of finding that whatsoever. That wasn't given dr dt, and I'm not asked for dr dt. So this is going to become a problem with solving it this way. We're going to kind of run into a brick wall. So we're going to get rid of this and just say, okay, well, I don't have dr dt, and that's going to implicitly come in here, and I don't have it. So what I'm going to do is use the tank info to do a substitution and get r out of there. I'm going to relate r and h, and I'm going to get r out of there. Okay, so you have similar triangles here, basically. You have this situation on the cone, there's a triangle, and then this is another triangle. Okay, and so similar triangles, one of our postulates is angle, angle, which really is angle, 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 but you only need 2 angles because the third angle is assumed due to your 180 limit on a interior sum of triangles. So both of these triangles here are sharing this tip angle, and the radii here would be parallel, so this could be a transversal line, so these would be corresponding angles, so they're the same. This right angle is the same, so these 2 triangles are going to be similar. So basically here, you could do a couple of things. This was, what, 20, this tank info, and this was 5. I wouldn't even bring the 8 in. I would just say, since these are similar triangles, I can go 20 is to 5 as H is to R. So 20R equals 5H, and then R is going to be 5H over 20, so R is going to be 1/4 of H. You could go in here and get this little H down here is 8, and do a proportion. 20 is to 5 as 8 is to this radius. Okay, and you would of course get 20R equals 40. R is 2, which we had predicted earlier. But don't sub the R in. You have to height is changing, radius is changing, volume is changing. So you can't sub into the changing variables yet. So this is sort of tempting to put that in there. But you could just say, okay, so R here is 1/4 of H. You'd have to write your equation just saying, okay, well 2 is 1/4 of 8. So this is what you want to use. Do not sub in the 2 yet. You have to do that post differentiation. All right, so volume then is 1/3. I'm going to write that as H over 4 if that's okay. Square it. H. Volume is 1/3 H cubed over 16. And now I don't have to use the product rule, which is awesome. So let's differentiate. Okay, so V prime is, all right, so we get 3 pi 48 H squared dH dt. So V prime was 12. This will be pi over 16 H squared, because that's the time stop for H, and dH dt is what I'm looking for. All right, so I've got 12 equals pi, that's 64. So that's 4 pi dH dt, divide by 4 pi. So 3 over pi. Height is linear, so meters per hour equals dH dt. All right, so a complete sentence, you would say, when the height is 8 meters, the height is changing at a rate of 3 over pi meters per hour. All right, last thing here is to answer, well, how fast is the radius changing when the water is 8 meters deep? All I need is an equation that relates radius and height. So I don't really need this equation anymore. I've got a lovely equation here, super simple, that relates R and H for this particular situation. So if you have an easier equation to use, you use it. So R equals 1/4 H. dr dt is what I'm looking for. 1/4. H differentiates to 1, so that's dH dt, which I just found. And so dr dt is 1/4 times 3 over pi. It is 3 over 4 pi. Radius is linear, so that's also meters per hour. dr dt. So let's talk it out here. When the water is 8 meters deep, the radius is changing at a rate, is increasing for both of these, we should say, is increasing at a rate of 3 over 4 pi, both in the denominator, 3 over parentheses 4 pi meters per hour. All right, so hope that makes sense, and I'll be doing another video on the second 2 pages, what the other classes are going to be doing next Tuesday. All right, thanks guys.